13.8 billion years ago, every particle, every atom, every bit of matter and energy that would eventually form galaxies, stars, planets, and even you existed in a condition so unimaginably hot and compressed that the physics we rely on to describe reality simply ceases to function. Yet the question that keeps physicists awake at night isn't about this explosive beginning, it's about what came before it. Was the Big Bang truly the absolute origin of everything, or was it merely a transition point, a doorway from something else that we're only beginning to glimpse through the mathematics of modern cosmology? Today, we're going to push beyond the conventional story of cosmic origins. We're venturing into the cutting edge of theoretical physics and cosmology to explore radical ideas that suggest our understanding of the universe's beginning is incomplete. These aren't baseless speculations, they're sophisticated scientific theories grounded in quantum mechanics, general relativity, and observational evidence. Over the next 2 hours, we'll investigate whether time itself had a beginning, explore the possibility that our universe emerged from nothing through quantum processes, and examine theories suggesting that reality extends far beyond what we can observe, perhaps into infinite multiverses or cycling through endless cosmic rebirths. If you've ever wondered whether the universe has always existed in some form, whether consciousness plays a role in shaping reality, or whether our three-dimensional world is just a projection of something more fundamental, you're asking exactly the right questions. We're about to dive deep into the most profound mysteries confronting modern science, where the boundary between physics and philosophy becomes wonderfully blurred, and where the answers challenge everything we think we know about existence itself. When we try to trace cosmic history backward toward the moment of the Big Bang, we encounter an insurmountable barrier that physicists call the Planck Epoch. This represents the earliest sliver of time that our current theories can meaningfully describe. At 110 million trillion trillionths of a second after the Big Bang, that's 10 to the negative 43 seconds, we hit what's known as Planck time. This isn't just a practical limitation of our instruments or computational power. It represents a fundamental breakdown in the mathematical frameworks we use to understand the universe. Think about what's happening at these scales. Einstein's general relativity has been tested across the entire cosmos, from the bending of starlight around the sun to the detection of gravitational waves from colliding black holes billions of light years away. It describes gravity and the curvature of space-time with breathtaking accuracy. Meanwhile, quantum field theory governs the subatomic realm with equal precision, predicting the behavior of particles and forces to more decimal places than we can measure. These two pillars of modern physics are both spectacularly successful in their domains, yet they become fundamentally incompatible when we try to apply them to the Planck epoch. At these extreme conditions, space-time itself loses its smooth, continuous character. Instead, it becomes what physicists describe as quantum foam, a seething, fluctuating structure where the very geometry of space and time bubbles and writhes at scales far smaller than any particle. Imagine space-time not as a stable stage where events unfold, but as a churning ocean of quantum activity, constantly creating and destroying microscopic wormholes, dimensional tears, and topological defects. This is the reality that existed during the Planck epoch, a reality so alien to our experience that our language struggles to describe it. During this earliest moment, the observable universe that now stretches 93 billion light-years across was compressed to a size smaller than a single proton. The temperature soared to 10 to the 32nd power Kelvin, a number so large it's almost meaningless. Under these conditions, the four fundamental forces we observe today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were merged into a single unified superforce. Matter and energy were interchangeable. Space and time, the very coordinates we use to locate events and measure durations, may not have existed as separate, distinguishable quantities. Even the concept of causality, the idea that causes precede effects, might have been suspended in this primordial state. What makes the Planck epoch so challenging is that we need a theory of quantum gravity to penetrate it, a mathematical framework that successfully merges general relativity with quantum mechanics. Despite decades of brilliant work by thousands of physicists, we still don't have a complete, experimentally verified theory of quantum gravity. String theory, loop quantum gravity, and various other approaches offer promising paths forward, but none has yet achieved the breakthrough needed to definitively describe physics at Planck scales. Each approach makes different predictions about the structure of space-time at these scales, and without experimental tests, we can't determine which, if any, correctly describes reality. Here's one of the most mind-bending implications of the Planck barrier. The very question of what happened before the Big Bang might be fundamentally flawed. If time itself emerged from quantum processes during or after the Planck Epoch, then asking what came before is like asking what's south of the South Pole. The question contains a hidden assumption that time existed prior to the Big Bang, an assumption that might simply be wrong. Time could be a property that emerged along with space and matter, making the notion of before meaningless in this context. Yet this doesn't mean we should abandon the question entirely. Theoretical frameworks suggest various scenarios where something existed prior to what we call the Big Bang, where our universe's origin represents a transition or transformation rather than an absolute beginning from nothing. These theories push the boundaries of physics into uncharted territory, but they do so by extending our best validated theories, quantum mechanics and general relativity, into extreme regimes. They're speculative, certainly, but they're grounded in solid mathematical foundations and our deepest understanding of physical law. Look around you right now. The space between the objects in your room, the air above your head, the vacuum of space between planets and stars, it all seems empty. But modern quantum physics reveals that this apparent emptiness is an illusion. What we call empty space, the quantum vacuum, is actually a roiling sea of activity at the subatomic level. It's filled with quantum fields that pervade all of space, and these fields are never truly still. They fluctuate constantly, creating pairs of particles and antiparticles that pop into existence from nothing, exist for infinitesimally brief moments, then annihilate each other and disappear back into the vacuum. These aren't hypothetical or metaphorical particles. They're real, measurable, and have observable effects on physical systems. Physicists call them virtual particles because they exist for such brief periods that they seem to violate energy conservation, borrowing energy from the vacuum and returning it so quickly that the universe's books balance before anyone can notice the discrepancy. This sounds like science fiction, but it's verified physics, confirmed by multiple independent experiments and observations. Consider the Casimir effect, one of the most elegant demonstrations of quantum vacuum energy. If you take two uncharged metal plates and place them extremely close together in a perfect vacuum, they experience an attractive force pushing them together. This force arises because the quantum vacuum between the plates can only support certain wavelengths of virtual particle fluctuations, while the vacuum outside the plates supports all wavelengths. This creates a pressure imbalance, and the plates are pushed together by the quantum vacuum itself. This effect has been measured with extraordinary precision and is now used in the design of certain microscale mechanical devices. Another manifestation appears in the spectrum of hydrogen atoms. When physicists measured the energy levels of electrons orbiting hydrogen nuclei with high precision, they found tiny deviations from the predictions of basic quantum mechanics. These shifts, called the Lamb shift after physicist Willis Lamb, who first measured them, arise from electrons interacting with virtual photons in the quantum vacuum. The electron is constantly being buffeted by these quantum fluctuations, slightly altering its energy. The measurements match theoretical predictions to incredible precision, confirming that virtual particles are genuine physical phenomena with real consequences. Perhaps most remarkably, the magnetic moment of the electron, the strength with which it responds to magnetic fields, has been measured to 13 decimal places. The theoretical calculation of this quantity requires accounting for the electron's interactions with every type of virtual particle that can exist, including virtual versions of all known particles and their antiparticles. The agreement between theory and experiment represents one of the most precise confirmations in all of science, and it absolutely requires the existence of quantum vacuum fluctuations. Now here's where things get cosmologically interesting. If the quantum vacuum can spontaneously create particle-antiparticle pairs, what prevents it from creating larger, more complex structures? What prevents it from creating entire universes? Some theoretical models propose that our universe itself began as exactly this kind of quantum fluctuation in a primordial quantum vacuum that existed before our Big Bang. Unlike the virtual particles we observe in laboratories, which quickly recombine and vanish, this cosmic quantum fluctuation underwent a process called inflation that we'll explore in detail shortly. This inflation amplified the fluctuation exponentially, making it permanent and evolving it into the expanding universe we inhabit. This possibility is reinforced by a remarkable feature of our universe's energy budget. When you add up all the positive energy contained in matter and radiation, then subtract all the negative gravitational potential energy that arises from mass attracting other mass, the total appears to be zero. Within measurement uncertainties, the universe's net energy content is consistent with nothing. This means that creating a universe doesn't violate energy conservation. The positive and negative contributions cancel out, allowing universe creation to occur without any net energy cost. From the perspective of quantum mechanics and energy accounting, universes might be free. If quantum fluctuations can create one universe without violating conservation laws, they should be creating them constantly. The same quantum vacuum that produces virtual particles around us every moment might be generating entire universes in regions of reality that remain forever beyond our ability to observe or interact with. This isn't wild speculation. It's a logical extension of well-established quantum mechanics applied to cosmological scales. The quantum vacuum might be eternally and everywhere producing universes, making reality vastly larger and stranger than the single universe we inhabit. These quantum origin models suggest that the question of what came before the Big Bang has a concrete answer. Before our Big Bang, there existed a quantum vacuum with its inherent fluctuations and quantum field properties. Our universe emerged from this substrate, not through any external cause or divine intervention, but through the same quantum mechanical processes that create virtual particles. The difference is that our particular fluctuation was amplified through inflation, transforming it from a microscopic quantum event into a macroscopic universe containing hundreds of billions of galaxies. In the 1980s, cosmologists faced several puzzling problems about the early universe that seemed to require incredibly fine-tuned initial conditions. The cosmic microwave background radiation, the afterglow of the Big Bang, has almost exactly the same temperature in all directions of the sky, differing by less than 1 part in 100,000. Yet according to standard Big Bang theory, regions of the sky separated by large angles could never have been in contact with each other, never had time to exchange energy and reach thermal equilibrium. How then did they end up at the same temperature? It's like finding that the air temperature is identical in 2 sealed rooms that have never been connected. Cosmic inflation, proposed primarily by Alan Guth and refined by Andrei Linde, Alexei Starobinsky and others, solved this and several other problems with a radical proposal. For an extraordinarily brief period, from about 10 to the negative 36 seconds to 10 to the negative 32 seconds after the Big Bang, the universe expanded exponentially fast, doubling in size every tiny fraction of a second. During this inflationary epoch, space expanded by a factor of at least 10 to the 26, possibly much more, growing faster than light can travel. This doesn't violate relativity because space itself was expanding, not objects moving through space, and relativity places no limit on how fast space can stretch. This exponential expansion solved the horizon problem by proposing that our observable universe grew from a tiny, causally connected region that had time to reach uniform temperature before inflation began. Inflation then stretched this small, smooth region to enormous size, so large that even light traveling since the end of inflation hasn't had time to cross it. This explains why the cosmic microwave background has uniform temperature. The different regions we see were once close enough to equilibrate before being swept apart by inflation. Inflation also solved the flatness problem. Measurements show that space on cosmic scales is geometrically flat, or very nearly so, rather than curved like the surface of a sphere or a saddle. In standard Big Bang theory, achieving this flatness requires the universe's initial density to be tuned to incredible precision, accurate to 1 part in 10 to the 60th power. Inflation makes flatness natural. Any initial curvature, whether positive or negative, gets stretched by the exponential expansion to undetectably small values, like how the surface of a balloon appears flatter as you inflate it to enormous size. Most remarkably for our purposes, inflation provides a mechanism for generating structure in the universe. Quantum fluctuations during inflation, tiny random variations in the inflation field driving the expansion, got stretched to cosmic proportions. These quantum variations became the seeds for galaxy formation. Regions that were slightly denser than average had stronger gravity, attracting more matter over billions of years and eventually collapsing into galaxies, clusters, and the large-scale cosmic web we observe today. The entire magnificent structure of the cosmos, every galaxy, every star, every planet, traces back to quantum fluctuations during inflation that were amplified to astronomical scales. Observations strongly support the basic inflation picture. Measurements of the cosmic microwave background by satellites like WMAP and Planck have confirmed that the spectrum of density fluctuations matches inflation's predictions with extraordinary precision. The pattern of hot and cold spots in the microwave background, representing denser and less dense regions in the early universe, has exactly the characteristics that inflation theory predicts. This represents a stunning triumph for theoretical cosmology, successfully predicting observations that weren't available when the theory was first proposed. However, inflation theory leads to profound and unsettling implications about reality's broader structure. Most detailed models of inflation suggest that once the process starts in any region, it doesn't stop everywhere simultaneously. Instead, inflation ends randomly in different locations through quantum tunneling events, creating bubble universes surrounded by still inflating space. This process, called eternal inflation, continues forever in most regions while stopping in isolated pockets that become distinct universes with their own Big Bang moments. Picture it this way: our Big Bang, the moment when inflation ended and our space became filled with hot matter and radiation, occurred in one bubble. But the surrounding space continued inflating, exponentially growing and producing new bubbles where inflation ended. Each bubble becomes an independent universe with its own version of space-time, causally disconnected from all other bubbles. The inflating space between bubbles expands so fast that nothing, not even light, can travel from one bubble to another. These universes exist simultaneously but can never influence or communicate with each other. Eternal inflation creates what cosmologists call the multiverse, an ensemble of bubble universes embedded in an eternally inflating background space. The mathematics suggests this process truly is eternal, having no beginning and no end. New bubbles constantly form as quantum fluctuations randomly cause inflation to stop in different regions, while the space between bubbles keeps expanding forever. This means our Big Bang wasn't the beginning of everything, just the beginning of our particular bubble universe within a vastly larger, eternally inflating structure. Even more strangely, the physical constants, particle masses, and possibly even the number of spatial dimensions might vary between different bubble universes. These properties are determined by how quantum fields settle into their lowest energy states when inflation ends, a process that can produce different outcomes in different bubbles. Some universes might have stronger gravity, different electron masses, more spatial dimensions, or entirely different sets of particles and forces. The vast majority of these universes would be sterile, unable to form atoms, stars, or any complex structures. But among infinite possibilities, every conceivable variation occurs somewhere. This eternal inflation picture transforms our understanding of cosmic origins. Instead of asking what came before our Big Bang, we should recognize that our Big Bang was one event in an ongoing, eternal process of bubble universe creation. There's no ultimate beginning to inquire about, just an eternal, self-perpetuating process driven by quantum mechanics and the properties of the inflaton field. Our universe, with all its galaxies and complexity, becomes a single bubble in an infinite foam of universes, most of them utterly unlike our own. Some versions of eternal inflation predict that every possible universe permitted by physics exists somewhere in the multiverse. This would include universes nearly identical to ours but with minor variations, universes with completely different laws of physics, and perhaps even universes with different logical structures governing cause and effect. Among infinite variations, every possibility is realized somewhere, making the multiverse unimaginably diverse and complex. Recent extensions of eternal inflation theory explore its implications for the far future as well as the deep past. If inflation is eternal forward in time as well as backward, then universe creation will continue forever. Bubble universes will keep forming throughout eternity, meaning that cosmic evolution never reaches a final state but continues producing new realities with new possibilities for complexity and consciousness. This paints a picture of an eternally creative, endlessly productive cosmos that will never exhaust its capacity for innovation and novelty. What if the Big Bang wasn't a beginning but a bounce, a transition from a previous contracting universe to our current expanding one? This idea, explored through various cyclic cosmology models, suggests that the universe undergoes endless cycles of expansion and contraction, with each Big Bang representing a rebirth rather than an origin from nothing. These models eliminate the uncomfortable question of first causes by proposing that the cosmos has no ultimate beginning, just an infinite succession of cycles stretching endlessly into both past and future. The ekpyrotic scenario, developed by Paul Steinhardt, Neil Turok, and collaborators, provides one sophisticated framework for cyclic cosmology. This model is rooted in string theory and extra dimensions, proposing that our three-dimensional universe is a brane, a membrane-like structure floating in higher dimensional space. The Big Bang occurred when our brane collided with another brane in this higher dimensional realm. The collision released enormous amounts of energy, which we observe as the hot, dense state of the early universe. The branes didn't annihilate each other, but bounced apart, with our brane expanding and cooling over billions of years. Each cycle in the ekpyrotic model follows a similar pattern. After the initial collision and bounce, the branes separate, and our universe expands for hundreds of billions of years. During this expansion phase, matter spreads out, stars form and die, galaxies evolve, and in some cases, life and intelligence emerge. Eventually, the expansion slows due to attractive forces between the branes, then reverses. The branes begin approaching each other again, and the universe enters a slow contraction phase, lasting another few 100 billion years. As contraction proceeds, the universe becomes progressively denser and hotter. Any structures that form during the expansion phase, galaxies, stars, planets, gradually break down as increasing temperature and density overwhelm the forces holding them together. Near the end of contraction, matter and energy become highly concentrated once again. But rather than collapsing into a singularity where physics breaks down completely, the branes collide in another controlled bounce, releasing energy that initiates a new expansion cycle. The universe is reborn, not from nothing, but from the compressed state of the previous cycle. This cyclic framework elegantly addresses problems that have long troubled cosmologists. The uniformity of the cosmic microwave background and the flatness of space emerge naturally without requiring the extreme exponential expansion of inflation. The approaching collision between branes creates uniform conditions across the entire brane surface, automatically producing the smooth, homogeneous state we observe. any irregularities from the previous cycle get smoothed out during the contraction and bounce, resetting the universe to a uniform starting condition for the next cycle. Each complete cycle in these models typically spans about 1 trillion years, far longer than the current age of our universe. We're currently in an expansion phase that will continue for hundreds of billions of years before gravity's pull, or whatever mechanism drives the cyclic process, reverses our expansion and initiates the next contraction. During this time, the universe will evolve through many epochs. Stars will form and die, black holes will grow and eventually evaporate, complexity will rise and fall countless times before the current cycle approaches its end. The accelerating expansion of our universe, driven by dark energy, initially seemed incompatible with cyclic models that require eventual contraction. However, theorists have developed sophisticated versions where dark energy's properties evolve over cosmic timescales. In these refined models, dark energy currently drives acceleration, making the expansion speed up, but its nature changes over hundreds of billions of years. Eventually, dark energy transforms from repulsive to attractive, or simply weakens enough that gravity regains dominance, causing the expansion to slow, stop, and reverse. This leads naturally to the contraction phase that sets up the next collision and bounce. Some cyclic theories propose that information or fundamental structures might survive the bounce between cycles. If certain properties of spacetime or quantum fields persist through the extreme conditions of the bounce, each cycle could build upon achievements of its predecessors. Advanced civilizations might discover ways to encode information in the universe's fundamental structure, creating cosmic archives that survive multiple cycles. This would allow for a kind of cosmic learning, where each generation of the universe becomes more sophisticated than the last, accumulating wisdom and complexity across multiple cycles. The cyclic approach offers an elegant solution to the fine-tuning problem. Rather than requiring a designer or invoking selection effects across infinite parallel universes, cyclic models suggest that universal parameters naturally evolve toward values supporting complexity through a process operating across multiple cycles. Universes that develop parameters hostile to structure formation would quickly cycle without producing interesting phenomena, but universes whose parameters allow complexity to develop might have properties that favor their own continuation or reproduction, leading to a cosmic selection process that naturally produces universes like ours. Critics of cyclic models raise important questions. How exactly does the bounce occur without violating known physics? What prevents the formation of a singularity during maximum contraction? How does entropy, which the second law of thermodynamics says must always increase, reset between cycles? Proponents address these challenges through detailed mathematical models, showing how quantum effects near maximum contraction might prevent singularity formation, how the collision process might produce entropy-reducing mechanisms, and how specific string theory configurations naturally lead to bouncing cosmologies. Recent observational programs search for evidence that could distinguish cyclic models from inflation. Certain cyclic theories predict specific patterns of gravitational waves that would differ from inflation's predictions. Future gravitational wave detectors might observe these signatures, providing evidence for or against the cyclic picture. Additionally, subtle features in the cosmic microwave background spectrum could potentially distinguish between different cosmological scenarios. Though the differences are small and challenging to detect, the philosophical implications of cyclic cosmology are profound. If the universe has no beginning and will have no end, just endless cycles of birth and rebirth, then existence itself becomes necessarily eternal. There's no first cause to explain, no ultimate origin to trace back to. Reality simply is, has always been, and will always be, cycling through endless transformations, but never truly beginning or ending. This perspective resonates with certain ancient philosophical and religious traditions that viewed time as circular rather than linear, suggesting that deep intuitions about cosmic structure might have preceded scientific confirmation. The 3 dimensions of space and 1 dimension of time that define our everyday experience might represent only a tiny fraction of reality's true structure. String theory, physics' most ambitious attempt to unify all forces and particles into a single coherent framework, requires space-time to possess additional dimensions beyond the four we perceive directly. These extra dimensions aren't mere mathematical conveniences. They're fundamental features of reality that profoundly shape the properties of particles, forces, and possibly even consciousness itself. String theory emerged from efforts to develop a quantum theory of gravity by replacing point-like particles with tiny vibrating strings as the fundamental constituents of matter and energy. The mathematics of string theory works only if spacetime has more than 4 dimensions. The most developed versions require 11 dimensions total, 6 or 7 more than we observe. These additional dimensions aren't visible because they're compactified, curled up into shapes so tiny that even our most powerful particle accelerators can't probe them. At every point in our familiar three-dimensional space, there exist these extra dimensions, microscopic but real, determining how strings vibrate, and thus what particles and forces we observe. The precise geometry of these compactified dimensions determines all the properties of our universe that we consider fundamental. The masses of quarks and electrons, the strengths of gravity and electromagnetism, the number of particle families, even the cosmological constant driving dark energy, all these emerge from how the extra dimensions are shaped and how strings vibrate within them. Different compactification geometries produce different physics, potentially giving rise to universes with entirely different laws and properties. Brane Cosmology extends this dimensional framework to cosmic scales. In this picture, our entire three-dimensional universe is a brane, a membrane-like structure embedded in higher dimensional space called the bulk. This bulk space might contain other branes, each hosting its own universe with potentially different physical properties. These parallel universes could exist just fractions of a millimeter away from us in the extra dimensions, while remaining completely inaccessible through ordinary three-dimensional travel. You could pass through the precise location of another universe and never notice it because your motion would be confined to your brain, unable to access the extra dimensions needed to reach the neighboring universe. When branes collide in the bulk, the impact releases energy that appears as a big bang from the perspective of observers confined to either brane. This provides an alternative mechanism for cosmic origins that doesn't require inflation, though it's compatible with it. The collision process naturally creates the uniform temperature and density conditions we observe in the cosmic microwave background. The energy released during impact heats up and energizes the brane, causing it to expand rapidly in its three-dimensional extent. As the branes bounce apart after collision, the hot, dense phase cools and expands, evolving into the universe we observe today. Brane collision models make specific predictions about observable consequences. They predict particular patterns of gravitational waves that differ from those expected in standard inflation. They might produce topological defects, cosmic strings, or domain walls, structures that could be detected through their gravitational effects or their imprint on the cosmic microwave background. Some versions predict variations in the cosmological constant across space that could be observed through their effects on distant supernova brightnesses. While challenging to test, these predictions make brane cosmology scientifically viable, offering observational signatures that could confirm or rule out the theory. The higher dimensional spaces of string theory might not be static. Some models propose that extra dimensions evolve over cosmic time. Our universe might have begun with all dimensions the same size, but as it cooled and expanded, 3 dimensions grew large while the others remained microscopic. Alternative scenarios suggest that additional dimensions might gradually unfold as the universe ages, potentially leading to dramatic changes in physics in the far future. If extra dimensions become accessible at accessible scales, it could revolutionize our technological capabilities and understanding of reality. String theory's landscape problem represents both a challenge and an opportunity for understanding cosmic origins. The theory allows for approximately 10 to the 500th power different possible configurations of the extra dimensions, each corresponding to a universe with different physical laws. This enormous number initially seemed like a disaster, making string theory unable to predict anything definite. However, combined with eternal inflation, the landscape suggests that all these possibilities might be realized somewhere in the multiverse. Each bubble universe in the eternally inflating space would have its own extra-dimensional configuration, producing a multiverse far vaster than even inflation alone suggests. Experimental tests of extra dimensions face enormous challenges but aren't impossible. Particle accelerators search for missing energy signatures that might indicate particles escaping into the bulk, or for modifications to particle interactions caused by extra dimensions. Precision gravity experiments test whether gravity behaves differently at very small scales, where extra dimensions might become accessible. Gravitational wave observations might eventually detect signals from parallel branes or observe deviations from general relativity predictions caused by gravity propagating through extra dimensions. One of the most intriguing possibilities involves communication across dimensional barriers. Gravity, unlike other forces, appears to propagate through all dimensions, not just along branes. This means that gravitational waves might travel through the bulk, potentially allowing signals to pass between parallel universes. Sufficiently, advanced civilizations might learn to modulate gravitational waves as communication signals that cross dimensional boundaries. Such communications might already exist in subtle patterns in cosmic gravitational wave backgrounds that we haven't yet learned to detect or interpret. The existence of extra dimensions raises profound questions about the nature of fundamental reality. If additional dimensions exist but remain hidden from our senses and instruments, what else might be real but unobservable? Does reality contain infinitely many layers of structure, each inaccessible from the others? Are consciousness and other aspects of experience associated with structures in dimensions we can't perceive? These questions push physics toward philosophy, exploring the boundaries of what we can know about existence through empirical observation. String theory and Brane cosmology suggest that the multiverse might be far more diverse than eternal inflation alone implies. Not only do different bubble universes have different values of physical constants, but they might have entirely different dimensionalities, different numbers of branes, and possibly even different forms of mathematics governing their evolution. Some universes might have time flowing in multiple directions, others might have no concept of time at all. Among infinite possibilities across both the eternally inflating space and the vast string theory landscape, every conceivable form of existence might be realized somewhere, making reality incomprehensibly richer than the single universe we inhabit. Everything you've ever experienced, every object you've ever seen, every place you've ever visited, exists as information encoded somewhere else. This radical proposal, known as the holographic principle, emerged from deep investigations into black hole physics, but has evolved into one of the most profound ideas in modern theoretical physics. It suggests that our familiar three-dimensional reality might be a topter, projection, like a hologram, of information stored on a distant two-dimensional surface. The very notion of spatial dimensions might be less fundamental than we've always assumed, emerging from deeper informational structures. The story begins with black holes and the information paradox. When matter falls into a black hole, it appears to be destroyed, vanishing behind the event horizon, and eventually crushed into the singularity at the black hole's center. This presents a severe problem for quantum mechanics, which insists that information can never be truly destroyed. Where does the information go? Stephen Hawking initially suggested it might be genuinely lost, violating quantum mechanics' fundamental principles. But physicists, including Gerard Hooft and Leonard Susskind, proposed a different solution. They realized that the information doesn't actually fall into the black hole. Instead, it gets encoded on the event horizon, the two-dimensional surface surrounding the black hole. Detailed calculations showed that a black hole's entropy, its information content, is proportional to the surface area of its event horizon, not its volume. This is bizarre from conventional perspectives. In ordinary systems, entropy and information content scale with volume. A larger box contains more gas molecules and thus more entropy than a smaller box. But black holes follow different rules, suggesting that three-dimensional space somehow emerges from information on two-dimensional surfaces. Juan Maldaceno's ADES CFT correspondence provided the first rigorous mathematical realization of holographic principles. This remarkable duality demonstrates that a gravitational theory in five-dimensional anti-de Sitter space is exactly equivalent to a quantum field theory without gravity on the four-dimensional boundary of that space. These aren't approximations or analogies. They're precise mathematical equivalences where every calculation in the gravitational theory corresponds to a calculation in the boundary theory producing identical results. You can solve problems using either description and get the same answer, suggesting they describe the same physical reality from different perspectives. Applied to cosmology, holography suggests our entire observable universe might be encoded as information on a cosmic horizon at the boundary of observable space. The three spatial dimensions we experience could emerge from quantum information processing on this distant two-dimensional surface. We perceive three dimensions because that's how the holographic information is reconstructed, but the fundamental reality exists as quantum bits on the boundary surface. Everything we've ever observed, from atoms to galaxies, would be holographic projections of boundary information. This holographic perspective offers revolutionary insights into the nature of space-time itself. Recent work suggests that space emerges from quantum entanglement patterns between different regions of boundary information. When quantum systems become entangled, meaning their properties are correlated even when separated, this entanglement translates into geometric distance in the emergent three-dimensional space. Strongly entangled boundary regions correspond to nearby points in space, while weakly entangled regions correspond to distant points. Distance and geometry aren't fundamental features of reality, but emerge from the quantum information structure of the boundary. The implications for cosmic origins are startling. The Big Bang would represent the moment when information processing on the cosmic boundary activated, transforming static boundary information into the dynamic, evolving, holographic projection we experience as space-time. Before this activation, the boundary information might have existed in some inactive state, containing the potential for our reality, but not yet generating the experience of three-dimensional space, time, and evolution. The question of what came before the Big Bang becomes a question about the state of boundary information prior to activation. Quantum error correction provides unexpected insights into holographic systems. The encoding of three-dimensional information on two-dimensional surfaces naturally includes redundancy that protects information from corruption. This redundancy functions like error-correcting codes in computer systems, ensuring that even if parts of the boundary information are damaged or lost, the bulk three-dimensional information can be reconstructed. This built-in error correction might explain why physical laws appear so stable and consistent, resisting disruptions that would otherwise create inconsistencies in reality's structure. Holography also offers new perspectives on consciousness and observation. If physical reality emerges from information processing on the cosmic boundary, consciousness might represent an especially sophisticated form of information integration that naturally arises in complex holographic systems. Conscious observers wouldn't be separate from the holographic projection, but would themselves be patterns in the boundary information, achieving self-awareness. The hard problem of consciousness, understanding how subjective experience arises from physical processes, might be reframed as understanding how certain information patterns on the boundary achieve reflexive awareness of their own existence. Testing holographic cosmology experimentally presents enormous challenges. Some models predict subtle corrections to gravitational wave propagation that advanced interferometers might eventually detect. Others suggest specific signatures in cosmic microwave background radiation that could distinguish holographic models from non-holographic alternatives. The deviations are tiny, requiring extraordinary measurement, precision, but they provide potential paths toward experimental verification or falsification. If reality is fundamentally holographic, it forces us to reconsider the nature of existence itself. The solid, three-dimensional world we experience would be, in a precise sense, illusory, a convincing projection of deeper two-dimensional information structures. This doesn't make our experiences less real in any practical sense. The projection is consistent, follows mathematical laws, and provides a stable framework for observation and interaction. But it does suggest that reality has layers of description, with the familiar three-dimensional picture being derivative rather than fundamental. Holography connects to digital physics and information theory, suggesting deep relationships between information, computation, and physical law. If the universe is holographic, it's also fundamentally informational, meaning that everything reduces ultimately to patterns of information processing. The laws of physics would represent algorithms governing how information evolves on the boundary surface. Particles, forces, and space-time would all be emergent phenomena arising from underlying informational dynamics. The holographic principle raises philosophical questions about the nature of observation and existence. If we exist as patterns in boundary information, what exactly is having our experiences? Are we the patterns themselves, or something additional that emerges from complex information organization? Does the boundary information possess some primitive form of awareness, or does consciousness only appear at certain levels of complexity? These questions blur traditional boundaries between physics and philosophy, suggesting that understanding the deepest nature of reality requires integrating insights from both domains. The relationship between quantum mechanics and consciousness has fascinated physicists and philosophers since quantum theory's earliest days. While early interpretations suggested that conscious observation might play a fundamental role in determining quantum outcomes, modern understanding reveals a more nuanced but equally profound picture of how awareness might connect to reality's deepest structures. The measurement problem in quantum mechanics, the question of how and why quantum superpositions collapse into definite states, continues to challenge our understanding and might hold keys to understanding consciousness itself. Quantum mechanics demonstrates that microscopic systems can exist in superposition states, possessing multiple contradictory properties simultaneously. An electron doesn't just have an undetermined spin direction until measured. According to quantum theory, it literally exists in a state where it has both spin up and spin down simultaneously. Only when a measurement occurs does the system collapse into one definite state, displaying either spin up or spin down but not both. This behavior is confirmed by countless experiments, most famously the double-slit experiment, where individual particles create interference patterns characteristic of waves passing through both slits simultaneously. The measurement problem asks why observation causes this collapse. Different interpretations of quantum mechanics provide different answers. The Copenhagen interpretation suggests that measurement inherently disturbs quantum systems, forcing them to assume definite values. The many worlds interpretation proposes that all possible measurement outcomes occur, but in separate parallel branches of reality that can never interact. Decoherence theory explains how quantum systems lose superposition properties through interaction with their environment, without requiring conscious observers to play any special role. Yet fundamental questions persist about why we experience one particular outcome rather than others, and what role, if any, consciousness plays in selecting which outcome manifests. Recent discoveries in quantum biology reveal that biological systems can maintain quantum coherence under conditions thought impossible for quantum effects to survive. Photosynthesis achieves nearly perfect energy transfer efficiency through quantum coherence effects that allow energy to simultaneously explore multiple pathways before selecting the most efficient route. Certain birds navigate using radical pairs in their eyes that maintain quantum entanglement long enough to detect Earth's magnetic field with extraordinary sensitivity. These findings demonstrate that quantum effects aren't confined to isolated laboratory systems, but operate within warm, wet, noisy biological systems. possibly including the neural structures supporting consciousness. Roger Penrose and Stuart Hameroff's orchestrated objective reduction theory proposes that consciousness arises from quantum computations in microtubules, structural proteins within neurons. They suggest that microtubules maintain quantum superpositions that integrate information across large regions of the brain, with conscious moments corresponding to events where gravitational effects cause the superpositions to collapse. While controversial and not widely accepted by mainstream neuroscientists, this approach attempts to explain consciousness's unity and apparent binding problem through quantum mechanical principles that could integrate information in ways classical neural networks cannot achieve. If consciousness involves quantum processes, it might actively participate in determining reality's structure rather than passively observing a predetermined world. Conscious observation might influence which possibilities become actualized through quantum measurement effects. This doesn't require mystical or supernatural mechanisms, just the possibility that biological systems can influence quantum outcomes through physical interactions. The act of conscious observation could help select which branch of quantum possibility becomes the realized reality we experience. The implications for cosmic origins are fascinating. If consciousness influences quantum processes, and if the universe's initial conditions were determined by quantum events, then the emergence of consciousness might retroactively influence the cosmic parameters that allowed consciousness to evolve. This creates a participatory universe where future consciousness helps determine past conditions, enabling consciousness. The anthropic principle becomes not just an observational selection effect, but an active process where conscious beings participate in selecting their own cosmic history through quantum measurement effects. Consider that quantum measurement effects might operate across vast scales of space and time. Advanced consciousness might learn to manipulate quantum processes directly, influencing quantum events throughout cosmic history. These influences could affect the quantum fluctuations during cosmic inflation that determined cosmic structure, helping explain why the universe appears so finely tuned for complexity, not through random chance or external design, but through quantum feedback loops, where consciousness helps create conditions for its own emergence. Future forms of consciousness might develop capabilities seeming impossible from our current perspective. Advanced civilizations might manipulate their own quantum states, accessing information from superpositions or influencing physical processes through measurement effects. Such capabilities could blur traditional boundaries between mind and matter, observer and observed. Post-biological intelligences might exist as coherent quantum systems, maintaining superposition states while remaining conscious, effectively inhabiting multiple realities simultaneously until choosing which possibilities to actualize. The connection between consciousness and quantum mechanics also raises questions about individual minds' relationship to cosmic processes. If quantum entanglement connects distant universe parts, and consciousness involves quantum processes, individual minds might be more interconnected than classical physics suggests. Boundaries between different conscious beings and between consciousness and universe might be less distinct than everyday experience indicates. We might all be aspects of a single cosmic consciousness, experiencing itself from multiple perspectives, connected through quantum entanglement, operating beneath awareness thresholds. Some theories propose that consciousness is fundamental rather than emergent, existing as a basic reality feature alongside space, time, and matter. In panpsychist views, all quantum systems possess primitive consciousness, with complex awareness emerging when basic conscious elements become sufficiently organized. This would mean consciousness has been present throughout cosmic evolution, influencing quantum processes from the earliest moments and helping guide universe development toward greater complexity and awareness. Quantum consciousness might provide mechanisms for information transfer transcending classical limitations. Quantum entanglement could allow conscious beings to share information instantaneously across vast distances, while quantum superposition might enable parallel processing impossible with classical neural networks. Advanced civilizations might exploit these quantum consciousness effects, creating collective intelligences operating as single entities while maintaining multiple individual perspectives. These possibilities suggest consciousness might play fundamental roles in cosmic evolution, not as passive observer, but as active participant in the universe's ongoing creation. Questions about what existed before the Big Bang might ultimately be answered by understanding consciousness's role in quantum cosmology, recognizing that awareness itself might be one of the universe's most fundamental creative forces. What if reality is fundamentally computational, with everything we experience emerging from information processing according to mathematical rules we interpret as physical laws? This digital physics perspective suggests that asking what came before the Big Bang is like asking what existed before a cosmic computer program began executing. This opens entirely new approaches to understanding existence itself, treating information and computation as more fundamental than matter, energy, or even space-time. John Wheeler's it from bit hypothesis proposes that all physical quantities derive their meaning from information, from binary choices, selecting specific outcomes from quantum possibilities. Particles, forces, and space-time itself would be emergent properties of underlying information processing rather than fundamental reality constituents. Every measurement, every interaction, every physical event would represent information processing operations in a vast cosmic computation we experience as the unfolding of space and time. Information theory provides powerful tools for understanding physical processes across all scales. The holographic principle demonstrates that information can be encoded more efficiently than classical physics suggests, with three-dimensional volumes fully described by information on two-dimensional surfaces. Quantum error correction shows how information can be preserved even when physical systems carrying it are disrupted or destroyed, suggesting information itself might be more fundamental and durable than matter and energy. Black hole thermodynamics reveals deep connections between information, entropy, and gravity, pointing toward information's fundamental role. A black hole's Bekenstein-Hawking entropy is proportional to its event horizon's area, not volume, suggesting that any space region's information content is finite and bounded by its boundary surface area. This area law for information storage appears to be a fundamental principle applying throughout the universe, implying reality might be structured as information patterns distributed on cosmic boundaries rather than filling three-dimensional volumes. If reality is fundamentally informational, physical laws would represent computational algorithms running on a cosmic computer system. Gravity might be a subroutine calculating how information patterns attract each other. Quantum mechanics might be the operating system managing how information can be accessed and modified. Physical constants, apparent fine-tuning, could reflect that the universe runs software specifically designed to generate complexity and consciousness, with constants representing carefully chosen parameters, optimizing the program's ability to produce interesting structures. The simulation hypothesis represents one extreme digital physics version, suggesting our universe might be a computer simulation running on vastly more powerful computational systems. While capturing popular imagination through science fiction, it raises profound philosophical questions about simulated versus real experience. If consciousness can exist in any sufficiently complex information processing system, distinctions between simulated and fundamental reality might be less meaningful than initially appears. Conscious beings implemented in software would experience genuine thoughts, feelings, and sensations, regardless of underlying computational substrate. Recent theoretical physics developments support computation being more fundamental than previously imagined. The ADS CFT correspondence demonstrates that gravitational physics in higher dimensional space is exactly equivalent to quantum field theory computations on that space's boundary. This isn't mere analogy, but precise mathematical duality, where every gravitational calculation has a corresponding computational algorithm producing identical results. Such dualities suggest distinctions between computation and physics might be artificial, both representing different perspectives on the same underlying informational processes. Quantum computation provides insights into how information processing might operate at reality's most fundamental levels. Quantum computers perform certain calculations exponentially faster than classical computers by exploiting quantum superposition and entanglement to process multiple possibilities simultaneously. If reality itself is computational, it might be essentially quantum computational, with the universe processing information in ways transcending classical computational limits. Quantum nature of microscopic physics could directly reflect quantum informational processes underlying all physical phenomena. Digital physics offers revolutionary approaches to understanding cosmic origins. The Big Bang might represent when a cosmic program began executing, transforming static information patterns into dynamic spacetime evolution. Before this computational moment, information that would become our universe might have existed as unexecuted code or dormant data in some vast information processing system. Alternatively, our universe might be one sub-process in an ECHES, enormous distributed computation, with countless other universes representing different computational tasks running on the same cosmic hardware. Information conservation principles fundamental to both physics and computation suggest all cosmic history is permanently encoded in reality's information structure. Every event, from quantum fluctuations to galaxy formation to consciousness emergence, might be preserved as information patterns potentially accessible by sufficiently advanced information processing systems. This cosmic information archive could serve as universal memory, preserving complete histories of everything that ever occurred. Information processing capability evolution represents one of the universe's most remarkable trends, progressing from simple chemical reactions to biological computation to technological artificial intelligence. If this trend continues, future information processing systems might achieve capabilities seeming impossible from our current Place 6 perspective, potentially including ability to manipulate reality's computational substrate directly or access information from parallel computational processes elsewhere in the cosmic computer system. Claude Shannon's information theory demonstrates that any message can be encoded in binary form, reducing all possible information to sequences of yes-no choices. If reality is informational, everything we experience from coffee's taste to distant starlight would ultimately reduce to patterns of binary information processing. Richness and complexity we observe would emerge from intricate organization and processing of these fundamental binary elements, much as complex computer programs emerge from simple binary operations. Landauer's principle establishes that erasing information requires minimum energy, connecting thermodynamics to computation. If the universe is computational, the second law of thermodynamics might be direct consequence of computational processes generating reality, with entropy increase corresponding to irreversible consumption of computational resources as the cosmic program executes. Digital physics provides new perspectives on quantum mechanics measurement problem. If reality is computational, quantum measurement might represent information processing operations, converting superposition states into definite computational outputs. Quantum mechanics' probabilistic nature could reflect underlying algorithmic processes determining how quantum information gets processed into classical computational results. Our universe appears exquisitely calibrated for complexity, life, and consciousness existence, with fundamental constants balanced so precisely that tiny changes would render atoms unstable, stars impossible, or chemistry forbidden. This apparent fine-tuning raises profound questions about cosmic origins and the relationship between physical laws and observers discovering them, challenging us to understand why reality seems so perfectly suited for beings capable of contemplating existence. Consider fundamental forces governing reality. Gravity appears exactly right to allow stars forming and shining for billions of years, creating stable conditions for planetary systems and biological evolution. If gravity was slightly stronger, just 1 part in 10 to the 40th power, stars would burn fuel too quickly, exhausting energy in millions rather than billions of years, never providing extended periods for chemical evolution and biological complexity. If correspondingly weaker, gas clouds couldn't collapse to form stars, leaving the cosmos cold, dark, and lifeless. Electromagnetic force demonstrates even more remarkable calibration precision. Its strength determines how tightly electrons bind to atomic nuclei, establishing fundamental scales for atomic sizes, chemical bond energies, and molecular structures. Change electromagnetic force strength by a few percent either direction, and either atoms couldn't form stable configurations or chemistry would be too unstable to support complex molecules like DNA, RNA, and proteins forming biological system bases. Strong nuclear force binding protons and neutrons into atomic nuclei displays perhaps the most remarkable fine-tuning. A 5% change either direction would eliminate either carbon or oxygen from the universe by making nuclear fusion reactions, creating these elements in stellar cores either impossible or too efficient. Without both carbon and oxygen, rich chemistry supporting biological complexity becomes impossible, reducing the universe to simple hydrogen and helium with no possibility for complex molecular structures. Most dramatically, the cosmological constant driving dark energy appears fine-tuned to an almost incomprehensible degree. Quantum field theory predicts this constant should be enormous, roughly 10 to the 120th power larger than observed values, causing space to expand so violently that matter could never clump into stars, galaxies, or complex structures. Instead, it has almost exactly the tiny positive value needed to allow cosmic structure formation while driving observed accelerating expansion, differing from theoretical prediction by 120 orders of magnitude in perhaps physics' worst prediction ever. The probability of all these constants randomly falling within life-permitting ranges is effectively zero, comparable to throwing a dart blindfolded from Andromeda galaxy distance and hitting a specific atom on Earth. This extraordinary precision has led to intensive efforts understanding whether deeper physical principles could naturally explain apparent fine-tuning without invoking design or incredible coincidence. One approach invokes the anthropic principle, which comes in several versions with different philosophical implications. The weak anthropic principle simply notes we necessarily observe a universe compatible with our existence, because incompatible universes couldn't produce observers capable of making observations. This reasoning becomes more compelling, combined with multiverse theories predicting vast numbers of universes with varying physical constants. Among infinite possibilities, some universes would randomly possess right parameter combinations for complexity, and these would be the only universes containing observers capable of noting apparent fine-tuning. Alternative approaches seek physical mechanisms, naturally producing fine-tuned constants without invoking multiverse selection effects. Some theories propose fundamental constants aren't actually constant, but evolve to current values through cosmic evolution processes. In these models, constants we observe represent stable endpoints of dynamical evolution rather than randomly chosen initial conditions. String theory offers another fine-tuning perspective, suggesting apparent precision might be explained by specific extra-dimension configurations in our universe. The string theory landscape is enormous, potentially including 10 to the 500th power of different possible universes, with different physical laws, particle properties, and fundamental constants. If all these possibilities are realized somewhere in higher dimensional multiverse, fine-tuning becomes natural consequence of observer selection among infinite alternatives. Understanding cosmic origins requires considering not just past but also ultimate universe destiny, as the two might be more intimately connected than conventional thinking suggests. Current observations indicate our universe is dominated by dark energy, driving, accelerating expansion, and will determine the cosmos's far future evolution. If dark energy remains constant, our universe faces heat death through eternal expansion. Over the next 100 billion years, cosmic expansion will carry distant galaxies beyond our observable horizon, leaving future observers with increasingly isolated views of space. Star formation will peak within the next few billion years, then gradually decline as gas supplies exhaust. Red dwarf stars will continue shining for trillions of years, but eventually fade too. After stellar death, the universe enters the black hole era, lasting from about 10 to the 40th to 10 to the 100th power years after the Big Bang. During this period, black holes will be dominant, gravitating objects, slowly accreting remaining matter and energy. Even black holes aren't eternal, gradually evaporating through Hawking radiation, with evaporation time inversely proportional to mass. However, this heat death scenario assumes dark energy properties remain constant. If dark energy strengthens over time, expansion could accelerate so violently it tears apart galaxies, stars, planets, and eventually atoms in a big rip scenario, potentially occurring within 20 to 30 billion years. Conversely, if dark energy weakens, cosmic expansion could slow, stop, and reverse, leading to a big crunch where everything collapses together in conditions similar to the Big Bang, potentially setting stage for cyclic cosmology. Advanced civilizations might not be passive observers of cosmic fate, but could actively intervene in cosmic evolution. Sufficiently developed technology might learn manipulating dark energy, creating artificial black holes for energy storage, or influencing spacetime's fundamental structure itself. The possibility of cosmic engineering opens extraordinary scenarios for the far future, where advanced civilizations create new universes through controlled vacuum decay or black hole formation. Our journey through cosmic origin theory frontiers reveals a universe far stranger and more wonderful than ancestors imagined, yet also shows deepest questions about existence remain as mysterious as ever. We've explored quantum vacuum cosmology, where universes arise as fluctuations in eternal quantum foam. We've examined eternal inflation, creating infinite multiverses of pocket universes. We've investigated cyclic cosmologies with endless cycles of expansion and contraction. We've delved into higher dimensional Brane cosmology, holographic reality, and consciousness' possible role in cosmic evolution. Each approach provides insights into what might have existed before the Big Bang, but none offers definitive answers to ultimate questions about existence itself. Why does anything exist rather than nothing? Why do mathematics and logic laws themselves exist? Why does consciousness have capacity to contemplate its own existence and reality's nature? These questions point toward mysteries that may transcend physics itself, touching deepest philosophical problems about being, meaning, and purpose. Yet perhaps these questions' persistence is itself significant. That reality continues surprising us, continues revealing new depths of complexity and beauty, might be among its most remarkable features. We aren't external observers of cosmic evolution, but integral participants in the universe's process of self-discovery. Modern cosmology reveals we exist during an extraordinary epoch in cosmic history. We live after complex atoms formed but before stars die, during the brief cosmic moment when intelligent life can emerge and contemplate the universe's origins and fate. We're made of elements forged in stellar cores, organized by biological evolution, and capable of mathematical reasoning, probing reality's deepest structures. The scientific enterprise itself represents one of the universe's most remarkable achievements. Through human consciousness and intelligence, the cosmos has developed ability to study itself, discover its own history, probe its own fundamental principles. Every astronomical observation, every physics experiment, every mathematical theorem represents the universe exploring its own nature through conscious beings emerging from cosmic evolution. This participatory relationship between consciousness and cosmos suggests boundaries we typically draw between observer and observed, between mind and matter, between self and universe, may be less fundamental than they appear. Quantum mechanics hints at deep connections between measurement and reality. Information theory suggests consciousness and computation might be more closely related than classical physics imagined. The holographic principle indicates space itself might emerge from more fundamental information relationships. If consciousness plays integral roles in cosmic evolution, then intelligence emergence might not be accidental byproduct of cosmic processes, but natural outcome toward which the universe tends. Anthropic fine-tuning of physical constants could reflect not divine design or pure coincidence, but deep connection between reality's structure and awareness possibility itself. Questions we've explored about pre-Big Bang scenarios remain at cutting edge of physics and cosmology. While we cannot definitively answer what existed before the Big Bang, the scientific process of investigating these questions continues, revealing new aspects of reality's structure and deepening our understanding of existence itself. Each theoretical framework we've examined represents humanity's attempt to extend knowledge boundaries into previously inaccessible realms. Future observations and theoretical developments will undoubtedly refine, modify, or potentially revolutionize our understanding of cosmic origins. Next-generation telescopes will probe the cosmic microwave background with unprecedented precision, potentially revealing signatures of pre-Big Bang physics. Gravitational wave detectors might observe signals from cosmic events occurring before our observable universe formed. Particle accelerator experiments could discover new physics illuminating quantum processes underlying cosmic evolution. Advanced civilizations elsewhere in the universe, if they exist, might already possess knowledge about cosmic origins far exceeding our current understanding. The universe might contain intelligence, exploring these questions for billions of years longer than human science has existed. Contact with such civilizations could revolutionize our understanding of reality's deepest structures and our place within cosmic evolution. Yet even as science advances and knowledge expands, existence's fundamental mystery seems to deepen rather than resolve. Each answer reveals new questions, each solution opens new problems. Each step forward shows how much further the path extends. This mystery's eternal character might itself be telling us something profound about reality and consciousness nature. Perhaps the universe is structured such that consciousness will always find new depths to explore, new questions to investigate, new mysteries to contemplate. The relationship between mind and cosmos might be inherently inexhaustible, with each understanding level opening access to even deeper levels previously inconceivable. This would make scientific exploration of existence not a process with final destination, but an eternal journey of discovery. Questions about what existed before the Big Bang ultimately connect to most fundamental questions about consciousness, meaning, and purpose. Are we conscious beings merely complex arrangements of atoms governed by impersonal physical laws? Or does consciousness represent something more fundamental, perhaps even essential to reality's structure itself? These questions bridge science and philosophy, empirical investigation and existential reflection. Modern physics suggests reality is far stranger, more interconnected, and more fundamentally mysterious than everyday experience indicates. Quantum mechanics reveals a universe where observation plays crucial roles in determining outcomes. Relativity shows space and time are dynamic and malleable rather than fixed and absolute. Cosmology demonstrates we exist within almost incomprehensibly vast and ancient cosmic evolutionary processes. Investigating cosmic origins represents one of humanity's highest intellectual achievements, requiring integration of advanced mathematics, sophisticated observational techniques, and profound theoretical insights. Yet it also represents one of our most fundamentally human activities, the drive to understand our place in the cosmos and existence's nature itself. Every culture throughout human history has developed origin stories, and modern scientific cosmology continues this ancient tradition using mathematics and empirical observation tools. As we stand at current knowledge frontiers about cosmic origins, we find ourselves in positions similar to early explorers standing at unknown continents' edges. We can see tantalizing glimpses of new territories beyond our current understanding, but the full landscape remains to be mapped. Theoretical frameworks we've explored represent our best current maps of this unknown territory. But like all maps, their simplified representations of reality undoubtedly more complex and surprising than any single theoretical framework can capture. The journey toward understanding what existed before the Big Bang is also a journey toward understanding consciousness, reality, and existence's deepest nature itself. Whether we find ultimate answers or discover the mystery is eternal, we participate in the most magnificent adventure possible, the universe's quest to understand itself through consciousness emerging from cosmic evolution. In contemplating these questions, we realize we aren't separate from mysteries we seek to understand. We're expressions of cosmic processes we study, conscious patterns in universal information structure, local concentrations of awareness pervading reality. Questions we ask about cosmic origins are ultimately questions about our own deepest nature and the source of our capacity for wonder, understanding, and conscious experience. The mystery continues, and we're privileged to be part of it. Every moment of consciousness, every scientific discovery, every flash of understanding represents the universe exploring its own infinite potential through awareness crystallizing within cosmic evolution. The greatest discovery might not be what existed before the Big Bang, but recognizing that consciousness itself is the universe's way of experiencing and understanding its own existence. Thank you for joining this exploration into deepest questions about cosmic origins and reality's nature itself. The journey toward understanding continues, and each of us participates in this cosmic adventure of consciousness discovering existence's mysteries. The questions remain open, the possibilities remain infinite, and the wonder continues growing with each step we take toward understanding the magnificent cosmic story of which we're all part.